Hey everyone. So today we're going to talk about something that's kind of the secret sauce of modern AI. It's not just about throwing more computers or, mountains of data at a problem. It's about smarter design. We're talking about AI architectures.
I mean, have you ever really thought about it? How can your phone just instantly find every single face in a photo? It feels like magic, right? Well, the answer isn't just, feeding it a billion pictures and hoping for the best. It's about teaching the AI how to see intelligently right from the get-go. And that is where the power of architecture comes in.
Okay, so to really get why this smart design is such a game changer, we have to go back to the beginning. We need to look at where AI started, with the default, you could say, brute force models.
And that brings us to this guy, the multi-layer perceptron, or MLP for short. This thing is the original workhorse of AI. Now, in theory, it's what's called a universal approximator, which is a fancy way of saying that if you give it enough power, it can learn to do pretty much anything. It's simple, it's elegant, and it's really the foundation for a ton of AI theory.
But here's the catch, and it's a big one. You've got this trade-off. On one hand, yeah, MLPs are simple, they're super easy to parallelize on modern GPUs, which is great, but, and this is a huge but, they are absolutely ridiculously data hungry. I mean, to learn anything even remotely complex, they need an almost impossible amount of data. This makes them super inefficient and crazy expensive for big inputs, like, say, high-resolution images.
And this really gets to the heart of the problem. To an MLP, an image isn't a picture of a face or a car or your dog. It's just a massive, jumbled up list of pixel values. It has absolutely no built-in idea that the pixel here is related to the pixel right next to it. It has to learn that basic common sense fact from scratch. And trust me, that is a monumental and kind of wasteful task.
So, right. How do we fix this? Is there a way to build an AI that doesn't have to learn everything from absolute zero? Well, yeah. And I think the best way to get our heads around the solution is with a little analogy. Okay, so picture this. Imagine that the perfect AI model for any given task, let's say finding faces, is like a single, tiny key. And this key is hidden somewhere inside a vast, pitch-black room. That room, it represents every single possible mathematical function the AI could ever learn. It's a huge space. Now, the MLP, our brute force model, its approach is like trying to find that key by slowly turning up a single, very dim floodlight. It's trying to light up the entire room at once. And sure, eventually you might see the key. But think about this staggering amount of energy, or in our world, data, you'd need to light up that whole massive space just to find one little thing. But a smarter architecture, it does something different. It doesn't try to light up the whole room. Instead, it makes an educated guess. It shines a bright, focused spotlight on a much smaller area, a spot where the key is most likely to be. And because of that, it finds a solution way faster, using way less energy. Okay, so this spotlight actually has a technical name. It's called an inductive bias. And really, all that means is it's a set of built-in assumptions that we give to the AI about the problem it's trying to solve. It's our way of giving the model a head start, of telling it, hey, look over here, this is the kind of solution you should be looking for. That way, it doesn't have to waste time searching everywhere. All right, so now we've got this really powerful idea, this concept of inductive bias. Let's circle back and see exactly how it solves our original problem. How do we teach an AI to actually see and understand what's in an image? And this chart, this just shows it perfectly. It's a fantastic illustration of just how powerful a good bias can be. So to learn a pretty simple function, a generic MLP, our old model, needs a ton of data points just to get it right. But look at this. A model with the right built-in assumptions, with that focused spotlight, it can absolutely nail it with just a few examples. The difference in how much data you need is it's enormous. So this brings us back to the crucial point for images. What's the most important assumption we can make? Well, it's that pixels that are next to each other are related. A pixel isn't an island. Its neighbors are probably part of the same object, or the same texture, or the same edge. So a much smarter approach starts to take shape. It's kind of like a two-step process. First, instead of trying to look at that one giant jumbled list of pixels, what if we broke the image down into small, local patches? And then second, we analyze those patches, but we do it with the understanding that what's happening in one patch gives us clues. It gives us context about the patches right next to it.
And this idea, this really simple idea of processing local patches, well, it turns out to be the foundation for one of the most important breakthroughs in the entire history of AI. Let me introduce you to the Convolutional Neural Network, or CNN. This is an architecture that was specifically designed with an inductive bias for grid-like data, which, of course, is exactly what images are. Its whole structure, its entire reason for being, is built around this idea of processing local overlapping patches. So what's the specific spotlight that a CNN uses? It's something called translation equivariance. Okay, I know, it sounds super technical, but it's a fancy term for a really simple, common sense idea. It just means that a bird is still a bird, whether it's in the top left corner of the photo or the bottom right. The identity of an object doesn't change just because its location does, and a CNN has that rule baked right into its DNA. So let's pull it all together. A convolution is really this powerful all-in-one package. It bakes in that common sense rule about location, it makes processing things in patches super efficient, and it actually learns to act like a set of really smart image filters. This design isn't just a little bit smarter. It's incredibly efficient, it's flexible, and that's exactly why CNNs became the absolute gold standard for pretty much all computer vision. And the incredible success of the CNN and its inductive bias, well, it just kicked off a complete revolution. Researchers everywhere had this light bulb moment. They realized, hey, wait a minute. If we can bake in the right assumptions for images, what's stopping us from doing the same thing for all sorts of other problems? So let's look at a couple of cool examples. First up, there's something called the unit. Its big idea is adding what are called skip connections. These are basically little shortcuts that let fine-grained details from the original image bypass some of the processing and then reappear at the very end. The inductive bias here is all about preserving detail, which makes it absolutely incredible for tasks like medical imaging, where every single pixel can make a difference. Then you've got ResNet, which uses a similar trick called residual connections. This little innovation was huge because it solved a major problem that was holding AI back, something called the vanishing gradient. And by solving it, it allowed these networks to become insanely deep. We're talking thousands of layers. The built-in assumption, the bias here, is kind of ironic. It's that sometimes the simplest path through the network is the best one, and that simple idea is what allows the model to learn much, much more complex patterns. And if you want to look at the real cutting edge, you've got models like NeRFs. Now, these are amazing. They build in assumptions about how light and 3D geometry actually work in the real world. And by doing that, they can take just a handful of 2D photos and reconstruct a completely interactive, navigable 3D scene. It's literally like teaching AI the physics of light. And this really brings us full circle, back to a central idea that's just perfectly summed up in this quote from Sarah Berry at MIT. The point is, it's not a choice. It's not more data or a smarter design. The real magic, the biggest breakthroughs, happen when you combine both. It's like having that powerful, focused spotlight, but using it to search through a really data-rich room. So where does this all leave us? It leaves us with a really fascinating question about the future. We've successfully managed to build our own common sense understanding of images right into our AI models. So what's next? What other common sense rules can we build in? The physics of motion? The underlying logic of language? Maybe even the rules of cause and effect? It really seems like the future of AI might be a lot less about brute force and a whole lot more about built-in wisdom. Thanks so much for tuning in.